So in corrosion thermodynamics, we're basically checking for the tendency for corrosion to that corrosion will occur, right? But in kinetics, you're actually measuring the rate at which the corrosion will occur, right? So then in the kinetics, we use this equation because the standard potential, right? Standard cell potential require that we use this way so that we can get the E standard, right? So we can get this, right? But here in kinetics, our aim is that we actually measure the corrosion. So like the corrosion is occurring and we are measuring it. So now to make our equation simpler to look at, because our interest is on the corrosion, we write it this way. We can write it's the same thing though. We have this, okay, and then we have Fe t plus 2e minus, right? So here our interest is on the second equation, right? Just to make sure understanding is related to what we are doing, right? So then that will mean that if so looking at this one here from what we are seeing, we know there's an equilibrium reaction, right? So then as from Faraday's law, we know that in order for us to check the mass loss, you could see that since if it goes this way, we have an anodic reaction, but if it goes this way, we have what cathodic, right? So this cathodic, this way is anodic, right? So basically means that if we have it in equilibrium, that will mean that the rate of the forward reaction is the same as the rate of the backward reaction, right? The same as saying the rate of the oxidation is the same as the rate of the reduction, right? So basically that means that the mass losses are the same. So from Faraday's law, we can write this. This is the mass because here is iron. Let's just write iron. And we have and then we have F. This is for the forward reaction, right? This one, right? And then which is the same as I. So this should be anodic, right? Forward reaction. This backward cathodic, right? Mass of the ion, and then we have F, right? And at this point, we clearly see that there are some things that are constant. We can take them out. So this are the same, right? So basically, this means that at equilibrium, right? So here we are discussion at equilibrium. We are doing right now at equilibrium at the moment. Right? So it means that at equilibrium, right? We have the current density for the forward reaction being the same as the backward reaction. Right? So that will mean that for the anodic, the same as current density for the cathodic, right? And we've seen that the current density is the current over the cross-sectional area. We've seen that already, right? Yeah. So then one thing that we do here is that because we are doing kinetics, we are trying to measure, right? But before we get to that, let's say this. And because the forward and backward reactions are the same, right, at equilibrium, we get to see that we call something net, which means that the net current density within this, if this we were to consider this to be our overall reaction, right, mean that the net current density through dielectric, because this case just one, is 0, which is what we call the net, right? And the net is basically the I cathode, sorry, I anode minus I cathode, right? Because you are doing corrosion here, our anode comes first, right? Comes at this side, just to show our interest. That's why we rearrange the reaction equation, right? And then there's something that we call what's the name? Exchange current density, right? It basically determines the rate at which the particular electrode we're talking about reacts to the environment, water, air, it could be anything, right? So we are seeing that at equilibrium, this exchange current density, which we write as this, is the same as the I current density for the anodic half, and the same as the current density for the cathodic half, right, at equilibrium. Yeah, because at equilibrium, these two are the same, and we are seeing that they are all the same like this, right? Okay, but because you are trying to measure, if they are the same, we won't be able to see what's actually happening what, right? So let's go. When we are trying to measure, meaning that we have the electrode here, so the electrode, right, would contain the metal I want to measure the corrosion rate, and this is what we call the reference electrode. We've seen different ones, right? So this is the basic setup that we use, right? That would mean that we potentially have to corrode the metal and then see what's happening, right? So enough for us to do that, what we do is that we apply something we call an external voltage source, right? So by doing that, we are doing something we call polarizing. We are shifting, right? Because here we are seeing the reaction is in equilibrium, but if we polarize it, mean that the reaction will no longer be in equilibrium. So then either oxidation will be more dominant or reduction will be more dominant, right? So it's the same way as saying that either the forward reaction will be more dominant or the backward reaction will be more dominant, right? So that's what we are doing. Okay. So if it happens that, so let's rewrite our equation. So we said because we are interested in the corrosion, we write it this way, right? Okay. And we have Fe 2 minus, and we have 2E minus, right? That's it. Yes, that's it. So in this case, we are interested in measuring the corrosion rate, right? So what happens? If we are interested in corroding the metal to see the corrosion rate, meaning that we actually do it this way, forward reaction, right? Before we have to make sure there's forward reaction. And now for you to do that, we must connect the electrode to a what? A positive, what's the name? External voltage source, right? And by doing that, it will mean that the reaction will go this way and then we corrode it. So when you apply a positive voltage source, so let's say we are applying a voltage source, right? Let's denote it this way. So in order for corrosion to occur and the reaction to proceed in this way, the applied voltage source that we attach, we apply to the cell must be greater than the standard, right? And we've already seen that for every reaction, reaction in this form, there's something we call a standard potential, right? So if you apply this potential here and it's greater than this, and it's greater than this standard potential here, right? Meaning there will be excess. And when there's excess, meaning that the reaction will be able to go this way and then end up corroding it, right? So that means that when we do it this way, we apply a voltage source that is greater than this standard electrode potential here. That means that we will get an excess potential, and that excess potential is what we call anodic overpotential, written this way, right? So anodic overpotential, right? So that excess potential is what will drive the corrosion to occur, right? Anodic overpotential, right? Which is written this way, right? Yeah. So if it happens that the potential that we apply to the cell, right, is basically less than the, what do you call it? It's less than the standard potential. So let's finish this. Meaning that when we apply and it's more than this, we have excess, right? So the difference, the over potential will be positive, right? So that will drive the corrosion. But then if we apply the voltage source and it's less than this E here, the standard potential, right? That will mean that when we do the subtraction, there will be a negative, right? So that will mean that the over potential will be negative. So we know it to be negative. When it's negative that way, that's what we call the cathodic overpotential, right? The cathodic overpotential, right? So this is what we have. Knowing this, what we actually do in the experiment, what's actually done in the experiment is that we actually on the same metal or the same sample that we're trying to test, we corrode it and protect it at the same time, but at different spots. So like if there's a sample, as we see here in the setup, within the same setup, there's a particular point on it that's undergoing corrosion and a particular point on it that's undergoing cathodic protection, right? So both are happening at the same time. And then we plot the values that we get from this, right? So what's happening is that the voltage that we are applying to such a setup is very small, right? So we've seen, you know, this is equal to iron, right? The voltage that we're actually applying to the setup is very small, so we end up getting current that are very, very small, right? So as a result, the current density will be small as well, right? So that's why on the x-axis we end up having what we call a log of I, right? Log of current density. So here, the actual overpotential is what causes, which the overpotential we already discussed that, right? So here we have the overpotential, right? So let's write it this way. The overpotential this side, right? So what's happening is that when we perform this experiment, there are values that we get, right? So we give it what you call voltage. The SS is what causes it to be anodic or cathodic, right? So then if we apply, as we've seen, the voltage and its excess more than the standard potential, we have positive. We get a line of a behavior like this, of this sort. So we have something like this, right? We're not doing the experiment, we're just seeing how it happens, right? So then all this side means here that the over potential that we apply within this region here is positive, right? So here is positive over potential, right? But then if we apply a potential that's way less, that's less than the standard potential in this case, right? In this case, then we end up getting over potential that's negative, right? So that's when we get something in this case, like here, right? And then when we plot at that side too, we get a different line behavior, right? Which is something of this sort. Something of this sort. Yeah. Right. And when we do this, what happens is that this overpotential as a function of other things, but you can see clearly that this side is the forward reaction, right? So this will basically be something like Fe, right? Going to Fe 2 plus 2 electrons, right? And this one will be the backward reaction. Those basically mean that if we have Fe, right, the reaction is favored backward, right? We are protecting it, right? Reduction. Fe 2 plus 2 electrons, right? So that's what's happening. So on the same sample, we are doing both these reactions at the same time, right? So that's what's happening. Okay. So when we do this, this is the behavior or the response current that we get, the current density that we get, right? Okay. Yeah. So then you can see that these two lines have each and every one of them, each one has its own slope, right? So looking at this one like this, clearly see that this one has a positive slope. Right? So that slope is, we will look at that later. That slope is what we use, and then again, this is experiment is what we call Tafel extrapolation, right? So when we do this, then we get a slope that's positive, right? Which is something like this B. We see, look at the values, and because this for the anodic side, just write beta A, right? Yeah. For this side, you see that has a negative slope, something like this, right? So the slope for this one here is beta cathodic. These are symbols, right? And then it has been seen, a lot of people have done a lot of work on this, and they've seen that there's a relationship between this slope and then the Dover potential applied, right? And it has been seen that for the anodic one, so let's see something like this. We have this, right? And then for the anodic overpotential is equal to the what do you call it, the slope for that one, and then we have log, right? And then we have this, the anodic current density, and then the exchange current density, right? And clearly we've seen that if it's at equilibrium, right, then mean that the overpotential is zero, right? So when at equilibrium, that will mean that these two are the same. So you make it 1 log of 1 is 0, it means the overpotential tends to 0, right? But here there's no equilibrium, right? So we have a value for this, right? Okay. And then this B2 has its own, the beta has its own representation. For the anodic part, we know that beta is positive slope, right? We've seen that. So from the work that they have done, they have seen that this beta is the same as 2.303 RT, right? And then we have this alpha, and then we have Faraday's constant, where R is wasn't it? R is the gas constant, the T is temperature, and this number of electrons, F is Faraday's constant, and this alpha here is just a geometric a symmetry what's the name, parameter, right? And what it says is that looking at this, we just assume that the reaction is simple, and because the reaction is simple, this factor here is just saying that which portion of the applied voltage is being used for, what do you call it, the anodic reaction, and which one is being used for the cathodic reaction, right? And in most cases, for simple reaction, we assume this alpha here to be 0.5, right? Yeah, that will mean that half, right? Half is used of the applied potential is used for the anodic reaction, half is used for the cathodic reaction, right? So 0.5 in this case, right? So like this. Okay. And then for the cathodic as well, we have a similar equation, right? Similar equation. So this is what happens. For the overpotential for the cathodic, right, is this way. So that too, it has its own beta constant, and these are constant we call the Tafel constant. These ones are called the Tafel constant, right? So in the Tafel extrapolation, right? So here is beta C equals for the cathodic half, and then we have log, and then here we have cathodic current density, and then we have exchange current density, right? But here the beta has a slightly different expression, right? You know the beta is negative because the slope is what, negative, right? For that anodic reaction branch, the cathodic reaction branch, right? So this BC is written this way, minus 2.303 R2. This is the relationship that they've seen, right? And they've given an equation to it. And we have this, the N is the same because of for the same reaction, right? And then we've said that this symmetry factor here describes the amount of the applied voltage that is contributing to the anodic reaction, right? And we are seeing for simple reaction 0.5. So that means that this is 1 minus alpha here, right? So if this is 0.5, then what we get inside here too will end up being 0.5, meaning that there is symmetry, right? Meaning that half of the applied potential is contributing to another reaction, half to cathodic, right? So that's what we have. And then this whole graph is what we are seeing here like this, right? This whole graph is what we are seeing. So it's just the same thing, right? Yeah. Okay. But one thing that happens is that when such an experiment is performed, we get values from these things, right? We get values from these, right? So we've seen what's happening over here already. And then when we plot these lines, there's a intersection point, right? And this intersection point, we know here is a log of current density, and here is the potential, right? And when we treat this and bring it down, we get something we call the I core, right? Which is the corrosion current density. And this is the current density at which corrosion begins to occur, right? And on this side, because here's potential, we end up getting what we call what's the name? This here is 0, right? And because it's 0, when we translate this to what's the name? Just the potential, right? We end up getting what we call the corrosion current, corrosion potential, right? Yeah. So that will mean that in order for us to be able to study a particular system and then determine the corrosion kinetic for that particular system, we do this experiment and we get values from these, right? Yeah, and these values it is with these values that we get to see, right? What is this? What is that? And then we determine this two E core and I core. The I core basically describes the rate of the corrosion, right? Because I is corrosion density. This small I here is corrosion density, right? And then this E core basically tells us the potential at which the corrosion occurs. Right? What this tells us is that when we are able to do this graph, right? At this I core, we get to know that the current density for the anodic half is the same as the current density. So that's at when we have I core. The current density in the anodic half is the same as the current density in the cathodic half, right? And we know that. And it's at this point that we have this corrosion potential, right? Yeah. All right. So that's it.